recording. Hello everyone, I hope you are doing well and you are ready for the lecture. Today we will have a general review of the design of the breakwaters, and also I will give you one example, complete example, and you'll see how to design the breakwater sections and for head and for trunk. Therefore, today is 28th of April. It is the week 9 of our lecture. We have live online lecture. If you have any question, please write to me. I will answer that. And let's see. Therefore, let's get started. As I mentioned, we will see first the review and the tables, the factors that we apply for the design of Rubble-Mound breakwaters. And a very complete example I show you, and you will design by applying the Hudson formula. First, let's see the overview. As I mentioned, the Rubble-Mound structures or Rubble-Mound breakwaters are the most commonly used breakwaters, and because of that, we see the design of this type of breakwater in this course. We had, for example, the conventional Rubble-Mound breakwaters that we are reviewing now, and there are another method that is berm breakwater, or that's can form by the waves. That's a new approach that is given by Van der Meer, Professor Van der Meer. It's something about perhaps 25 years that it's another method offered. Therefore, we focus here on the conventional Rubble-Mound breakwater design. The conventional Rubble-Mound breakwater consists of, let me highlight for you, consists of a core which has a large volume and at least a filter layer, and also armor layer. Armor layer is protecting the breakwater against the wave. The role of filter is to protecting the core not be washed or scored by the wave through the armor layer. And the material of the armor layer are the biggest size. And filters layers, the material size are bigger than core but less than armor layer. Here we see one section of one breakwater. You see the shaded one is the core. The core has actually a small size material, but the volume that is maximum. And we have another layer that it is, for example, here, this layer, it is a filter layer. The role of filter layer is protecting the core. And the other layer, which is actually is armor layer, that's at the external face of breakwater. which is the role of that is making stable the breakwater against the wave. Here in this slide we see how they construct the breakwater from land.
Currently the only person in this conference.
It means that they use the dump truck and cranes and grabs to handle, transport, and placing the armor layer, the filter layer, and dumping the core material by dump truck. Here you see plan of a small harbor that they use the Rubble-Mound Breakwater structure type. For example, here you see the armors, they are made of stone. They are stone. Here you see some other armor type, which is concrete, and it is tetrapod. Now we go to see the design of Rubble-Mound Breakwater. For the design, we use the Hudson formula. Hudson formula is an old formula which is proposed perhaps more than, I would say, 70 years. They modified a little, but actually the main skeleton of that is there. In this formula, we calculate W, which is the weight of unit armor. And in this formula, we use WR is unit weight of the armor layer. If it's a stone, is something between, I don't know, 2 to 3. If it's concrete, it's something between about 2.4 to 2.5. And again, the most important parameter is the wave height. We have different wave heights categories. For example, we have significant wave height. We say H1/3 or H33%. Previously, they applied significant wave height here. And then I think it's more than 20 years that the code is changed and they apply H10%. They use bigger wave height. And then we have KD, stability factor, which depends on the types of armor, the shape of that, and depends on the, for example, for concrete armors, this KD is bigger. Therefore, we need a smaller size of the armor units. And we have SR, which SR is the ratio of WR over WW. WR is unit weight of the armor layer, the material of that, and WW is the unit weight of water. Because this is a ratio, you can use both of them as density or the, for example, the unit weight. And there is theta. Theta is the angle of the slope section of armor layer. Let me show you in another slide. Yes, here if I show you, theta is this angle. angle between the armor layer and horizontal. And in the other side, in the lee side, when we have, this is harbor side or lee side. The other one is sea side, from the sea. Therefore, we have lee side and sea side. You see that in the side of sea or seaside, we need armor. But for the size of in the side of the lee, we don't need armor. Filter may be enough. Therefore, we'll see later how we design that. Yes. Now, let's see what is KD. KD is given by the US Army Corps of Engineers, and then this is summarized here. This is based on different tests. For example, you see the first column, the armor units are listed. Different things. We have quarry stone, we have tetrapod, we have quadrupod, 3-bar, Dallas, we have modified cube, we have hexapod, we have 3 bars, we have a lot of different models. And the second column shows the number of the layers. How many layers we have? For example, in the armor layer, perhaps we have 2 layers. In filter, perhaps we have 2 or 3. We can change the size of them as well. And then how they are placed. They are placed randomly or they are especially placed. Depends. These are depends on that. And you see that we have here 2 different columns. One here from here to here, and the other from here to here. What are the difference? Difference is for the first one, we calculate, we give the thing for trunk of the breakwater. The second one, give the values for head of the breakwater. Head of breakwater should be heavier, should be stronger, because the sections in trunk, they are supported by the other section, but the head is supported by nothing. After the head, we have water, and this is subjected to very strong waves. And then you see here the last column for different tests, they use different slopes or angles. Cotangent theta is the slope, and theta is angle that we discussed. You know, for example, for rough angular, we have 1, 2, 3 different slopes. The result also we have. For the 3 bars, everything, you know, they have different slopes are given here. And we saw that we have different types of armor units. The KD of Dallas is very high, is very good and used. We have tetrapod is common to use. We have 3-bar that is common to use. We have modified cube and the other types. Quadrupod here we have, and you see some star bar is has very close shape to the Dallas. And there are some famous, they are not. Why they are different types? Because if you want to use them, you should pay the patent fee. For some people prefer to use their own, or they generate more and get patent. Now let's see the overall concepts and then equations for design of Rubble-Mound Breakwater. Here we see how we calculate the weights of core, filter layer, and after that armor layer. All these values is given according to the recommendation of the U.S. Army Coastal Engineering Center. We have SEM, we have Shore Protection Manual, and more publications from there. You can search internet, you can buy some of them, you can download some of them and use them. For the design of the breakwater for layers, we need the thickness of armor layer, the thickness of filter layer. We use this formula, which we use N, the number of layers in armor layer, K delta, which is a factor we find from a table I will show you. WA is total weight of one armor unit, and W lowercase or small a, this is the unit weight of the material of armor layer. For filter, we have the same formula. Therefore, when we calculate W from Hudson formula, that is actually WA, the weight of armor unit. And if we divide that by 10, we find the weight of one unit in filter. And RA, as I mentioned, and RF, they are thickness of armor layer and filter layer. Therefore, we calculate all of these values and we sketch the section of the breakwater. This is a typical section of breakwater using for harbors. This special sketch by the slopes, by something, is given by a Professor Dr. Noban in his thesis. He used that and calculated all the, for example, materials and then a lot of things based on this section. We use that one. It's a very practical. As I mentioned, in the lee side, in the harbor, we don't have the armor layer. In the sea side, we have armor layer. And a very important part that is recently very emphasized, perhaps more than 25 years, that's a berm. When you put a berm here, it makes stable the armor layer and totally the breakwater. And the weight of that is W over 10, like the size of the filter layer. You see here, for armor layer, the weight is W, here shown here. And for filter layer, as is recommended by the US Corps of Engineers, this is W10. But for core level, which is the main body of the section, is between W over 200 to W over 4,000. And we have C here. C is the width of the crown or the crest here. And we have D, this is depth that we use in the design from the design, maximum design seawater level that Dr. Novan has fixed that one on the crest of the core. Is on the crest of the core, this level. Why? Because when you have this one, the dam trucks can work on that on all times. Otherwise, they have problem. These are dam trucks can go and, for example, handle the material. If we have high water level or low water level, always this is actually nearly for design dry, and the dam truck can go there. Otherwise, it cannot go there. It goes to the sea. The minimum, as I mentioned, crest width is shown in the figure by C, but the US Corps of Engineers give by B. It has a formula like this: N, the number of layers in any layer, in armor or in filter, and then K delta W, this is the armor layer unit weight of 1 unit of that armor layer, total weight of 1 unit, and WA, as we discussed, it is unit weight of the material of armor. Therefore, N is the number of the armor layer in armor layer. Perhaps armor layer its own has 2 layers, 3 layers, but mostly 2 layers or 1 layer. Therefore, as I mentioned, we use here K delta, but we didn't see what is K delta. Let's see what is K delta. K delta is given in table here. You can see the value of K delta. This is the corrected. I corrected. It was KD. I corrected to K delta. That's correct. Therefore, depends on the armor layer type. The first column shows that. As I mentioned, we have quarry stone, we have tetrapod, quadripod, hexapod, 3 bars, dollars, and etc. 3 bars. And second one give again us the number of layers in that layer, the placement type, and finally we find K delta. And we can find 1% for porosity of the layer. For example, in armor layer, you know, we have a stone, but between the stones there are air, there are gaps, there are void. Therefore, it calculates how many percent void there is there. And because of that, if we have the length and height and, for example, the width, we have total volume multiplied by percentage of this one. We see the empty part, and 100 minus 38, for example, percent give you the full part, and you can estimate the quantity of material. You know, in this table, you see there are some 1, 2, 3, actually these values 4, 5, just give some more information about who has given that and how, etc. Here it's listed here. Another table that we have, this is showing the damage to the structure, to the breakwater. What does it mean? It means, yes, we can design a breakwater very strong during the life of the breakwater. Never there is any damage, but it's not economic. We should apply a very big wave height, and the stone sizes or armor sizes are very big. Actually, we accept, okay, when in the normal case, up to 5% the damage, we accept that. And during the operation period, we repair that. For example, okay, one wave comes after 10 years and moved some stones or armors, concrete armors, everything. We can replace that. We can repair that. Sometimes at the beginning of project, we don't have a lot of money. You say, okay, we don't have money. Let's put and apply this smaller sizes of armor. And if there is damage, we repair during the years. 1 year, 2 years, everything, we change some of them. Some even breakwaters has permanent repairment. They change this one, wave comes and destroy another part and then replace, and because they divided the budget in two parts, one at the beginning, one in the operation period. If you put a big budget at the beginning, less repair and less budget you need for repairing of that. Inverse, if you put lesser budget, you need more repairing budget later. Actually depends on you. And this table gives the ratio between the edge design, what you have considered, perhaps you consider 10% damage, 15% damage, because you don't have a budget, enough budget now. And you compare edge with HD0 when the case that we say there is no damage. It means between something 0% to 5% damage, we have, you see, all of them 1. It means even for not damage case, we accept 5% damage. This is all, this column is just 1, you see that. Okay, if we accept 5 to 10% damage, we calculate H over HD 1.08. Therefore, if your H was 5 meter, by using 0.8, you find, for example, what is HD? Perhaps it's 4.8, I don't know. We have one example, later we see that. For any other case, you calculate. You compare the design edge and when the design edge, there is no damage. Therefore, in the formula, H is considered the wave height in calculation of the armor error. In the calculation, when you calculate, you design that. This is the, for example, H you apply to the design. Let me change the color. And HD equals 0, consider the wave height with 0% of damage. And now we see one example. As an example, if H, the design H, is 5 meter, and we have quarry stone rough material. Rough, it means sometimes it's sharp, sometimes it's rough. And then damage percent is 10%. You design for that. Now let's calculate what is edge that has no damage. Then you see that H over HD0 is 1.8. You found this from the table. Let's go and see. Therefore, the condition is quarry stone rough, damage 10%, and that's what we have. Quarry stone rough is the second one, this one. Quarry stone rough. And damage 10% is the second column here. Therefore, we find from that table 1.08. For quarry stone, the corner of that, the edge of that is rough, and we accept up to 10% damage. 10% damage. We find a value of 1.08. Because of that, we have one value of 1.08 here. We found from that table. Therefore, if you put H5 here and 108, we find HD equals 4.63 meters. Therefore, we can say when we have H equals 5 meters, we have for a designed breakwater 10%, 5 to 10% damage. If we don't accept any damage, we should not design for 5 meters. For no damage case, we should design the breakwater for a height of 4.63 meters. It means less height, less damage. Bigger size of height, we have more damage. Therefore, that table gives for different values. In this table, we see the density of the armors on the land. How many per square meter we have? We see the number of armor units per unit area, are estimated by the formula given by U.S. Army Corps of Engineers, 2011 in CEM, Coastal Engineering Management. Therefore, you see that NA, in this formula, we should find NA, or NA over A. This is the density. It's N, the number of layers, armor, if you wanted how many armor, how many, the number. We should calculate from this formula, and you see that here, the porosity, the percentage we have. Do you remember the first one was 38%, 38 over 100, and WA over W. This is the unit weight, and this is the armor unit weight, total of that. And NA represents the required number of armor units for a given surface of area A. The K delta layer also is used, and P can be calculated from the table that we saw that. Now let's get back to the table. I'll show you again. Here, no, table 2. This is table 2. We can find K delta from here and porosity P from here for different. So this is table 2. This is table 3. We can find, I think, change this one. This is table 2 actually. This is table 2, not 3. I will change later the slide. Okay. We saw this one. What was that? Perhaps it was right. Let me see. No, this is here as well. This is table 2 as well. Because I changed the number of tables. And now let's see one example. Find the weight of armor units, filter layer units, and core unit sizes for trunk and head of a breakwater. You should have, for example, design first for trunk and then for head. The difference is mainly KD are different for trunk and head, and also head is symmetry. In lee side and C side and lee side they have the same form. Actually, lee and C they have armor in both sides, even on the crest. And sketch the related section of the mentioned breakwater with the following specification. Wave height is given to us. Which wave have? With edge of 10%. It means the highest 10% because wave height is an spectrum. We have different sizes. One day H is 0, one day is 2 meters, one day is 10 meters. North Sea, one day is 50 meters. In Persian Gulf, one day is 0, one day is 2 meters, 5 meters, one day is 12.5 meters. In the Gulf of Mexico, sometimes it is 0, 2 meters, some days 16.5 meters, for example. In Caspian Sea, it goes to 21 meters sometimes. Depends, because the return period of 100 years we calculate. Therefore, during 100 years, one very top comes. Which one we should select? We perform one spectrum and we consider H1%, H10%, H33%, and so on. Therefore, this is H10%. It means that not the toppest. It is among 10 top, or is at the 10th percentile, which is 5 meters given to us. I told you previously, US Corps of Engineers in shore protection, it proposed, I don't know, perhaps 30 years ago, 35 years ago, it was proposed significant wave height, and then they changed to H10. The type of armor we selected. Why? Depends on can we find a very good mine of a stone there? This is one question. Yes, we can. Okay, can you, for example, when you are making them, can you make a big size when separating from the, cutting from the mountain, etc.? Sometimes yes, sometimes no. Okay, if you, for example, have one piece of 50 tons, 60 tons, can you lift that? Can you transport that? These are all the things. Sometimes the wave is high, the wave height is very high. Therefore, we should have high stones, quarry stones. Sometimes it's impossible. Therefore, we shift to the concrete armor units. And then between different types of concrete armored units, you saw that there is tetrapod, Dallas, there is 3-bar, there is quadripod, there is modified cube, etc. Therefore, here we selected the Dallas. It has very good KD, where its stability is very good. And wave condition, where is the breakwater? We have breaking wave there or not? If we don't have breaking wave, the units are smaller. If we have breaking condition, break is storming, you have a lot of impact, you should have the bigger size. And seawater unit weight and density is not one, it's more than one, because there is, I don't know, salt, there is other ions, and some lakes even there is more. I told you, in, for example, the Lake of Urumiyeh in north of Iran is 1.16. In Lake of Death, it's more than that. In Lake of Death, you can sit on the water and read the newspaper. It's very heavy, but it's some exaggeration, but it's right. Now let's see the solution. First, we see for the trunk. For the trunk, KD is different. Let's calculate KD. How we find 15.8 for that one? We go to this table. You see that for in the first column, we should select the armor unit. If you want bigger size of this table, you can go to previous slides, and that's bigger size. If you can see here is okay. And then we selected the Dallas. Therefore, we are in this row. The number of layers is 2. Therefore, we are here too. Actually, we don't have other option because the test gives us this result. If there is 1 layer armor, we should use the same value. If it is 2 layers, the same. Even if 3, the same. And what is the placement method? Is random. Again, we don't have any other method. It especially is placed. We should do the same because we don't have any other tested value. And okay, this is for the first column, second column, and third column. And after that, we see the condition of the wave. The condition is breaking. When it's breaking, before that, first is trunk. We select trunk, not head. This is head, but it's trunk. We can select the trunk. In trunk, we have 2 columns, breaking wave, non-breaking wave. Our condition is breaking wave. Therefore, we should go here. Therefore, here come down and horizontally Dallas to random. You go here. And vertically from the breaking wave for trunk, come here. And finally, you find 15.8. This is KD that we found here. Therefore, this was the first step. In the second step, we should apply the formula of Hudson. Hudson formula, we should calculate another important ratio, which is SR. The ratio of armor layer unit weight and water unit weight. The armor is concrete, we put 2.5, perhaps it's 2.45, because most probably at the beginning the Dallases were not armed. After the collapse of the breakwater of Sines of Portugal, they changed and they put some reinforcement inside. Therefore, if it's reinforced Dallas, we can put 2.5, that's okay. And for water, as I mentioned, we had this value. The SR gives us 2.433. Therefore, we apply here. And -1 has an effect of power 3, like H. And we applied everything, and cotangent theta, as you remember, was given as 2. We put here KD. This is the unit weight of the armor. This is the wave height, H10, 10%, and power 3. We find the weight of one unit armor, one armor unit, about 3 tons, 3.33 tons. And from here, for calculating B, the width of crest, the crest width, we need K delta. K delta we find from this formula. Again, we go to the armor unit column. We see our case is the loss. Therefore, the number of layers again is 2. Is random place. Therefore, from here we go horizontally, and K delta will be 0.94. If we continue, we will find the porosity percentage, which is 56%. Therefore, from table we found K delta, we found porosity percentage, and then we put in the formula of B and we find the other values. We applied those values here and everywhere. We found B, the crest width, that in the section that we saw and Dr. Fatima proposed, it's written C, the same. Now, the thickness of layers we should calculate for armor and for core, for filter. For core is not needed. RA for armor, RF for filter. We use the same, how many layers we have, 2, K delta, we found WA over W. W, capital A is total weight of armor unit, is 3 tons, 0.36. The other one is unit weight of that. And similar to that one, for how many layers we have for filter, what is K delta for that, what is the material, because material is different, and also what is the WF. Actually, WF is WA over 10, proposed by US Corps of Engineers. WF depends on the material of the filter layer, which is, for example, a stone is. Here we calculate RA, which is similar to that the B, like B, similar to the B that we had at top. Again, we put here the value of it was K delta, the other values, and we find RA in meters. RF, for finding RF, we need WF, and WF, as I told you, is WA over 10. What is the armor unit weight? We divide by 10, we find for filter. And then I estimated that for not very strong stones is minimum 2.2, even is less. We found in the south of Iran some, it was Shengel, the name was Shengel. They were very pure and even 1.9, but 2.2 is good. But a stone should be more than 2.5, 2.6, 2.7, 8. We apply the formula, the values, and then we find the RF, the thickness of filter. Therefore, we found the thickness of armor layer, and we found the thickness of filter layer. And here we see the density of armor units, how many we have per square meter, and A. If you apply A1, it gives us how many armor per square meter. And when we apply the same value, K delta, P, WA, W capital A, or W, they are the same, we find something 0.3 number over 1 square meter. It means that one of them take more than 1 square meter. Inverse of that give you what is the area of them. They are big. On 1 square meter, we cannot put them. You can calculate the size of that. And this is the section of the breakwater that we designed. For our layer, we found 3.36 tons. For filter layer, which it was W over 10, armor layer were here, for example. W over 10, we found W over 10 equals less than half ton, 0.336 tons. And for core layer, they are mixed between bigger size, which is W over 200, which is something about 17 kilogram. It means 20 kilogram, you know, is a small size. And the smaller size, W over 4000, is even something about 1 kilogram. Therefore, the core material is a mixture of material between 17 kilogram to about 0.8 kilograms. Take about between 20 and 1 kilogram. Therefore, these are easily can handle, transport, damped by the trucks. And as I mentioned, this form is normal, they used, but applied by Dr. Norman in his thesis for calculating the other things. Don't forget one important part is berm, toe berm. And toe berm is again W over 10, the same size as filter. What we should fix now for finding the depth of this one, D, from the crest of the core to the seabed, D. Actually, it is between the maximum design seawater level, which actually we consider mean high water level, because we have high water level, we have mean high water level, we have low high water level, and here we have low high water level here. Low high water level, high low water level, mean low water level. We have 6 different definitions here, because sometimes it goes here, sometimes here, here they are different. And here even we have higher than here. High level is higher than the design one. It means when dump truck wants to go here, if this is dump truck, for example, dump truck goes here, perhaps in 1 month, 1 day, or 5 hours, 2 hours cannot work because the water is higher than that level. But doesn't matter. We cannot go to the level low water, never they can go there. Here, we use that. Why? We can design the, for example, the high level of the breakwater to the highest level, but it's not economy. If D increases, the value of D increases, you see the area of trapezoidal of the core and the material increase very high. It's sometimes power 3 of that, or at least power 2. We should calculate that. Therefore, we don't increase the level of the crest of the core too much because it's not economic. We accept, okay, during 1 month construction period, or totally if the duration is 1 year, okay, we accept totally some 5 hours, 2 hours, we cannot work. Otherwise, we should pay a lot for material and even go for work increase. Therefore, we calculated D and C. You see that it was B, the crest width was 3 meters plus the breaking each 50 meters. Parking, we have parking there. You know, we didn't put here 7 meters from C from here to here. Why? Because normally 2 dump trucks should pass. One goes and one comes. Otherwise, we should stop the work. One dump truck goes to the, I don't know, head and dump his materials, comes back, the other goes. No. In that case, the construction of breakwater perhaps takes 5 years. We wanted in the same time, we have on the breakwater perhaps 2 or 3 or 4 dump trucks going on that. What is the solution? Either this C should be 7 meters that they can pass easily, or if we put 3 meters as we had considered here, we should put each 50 meters one parking. It means that C at each 50 meters is bigger, is 7 meters, and one can stay there. When the other dump truck pass, the first one can continue. These are the things that in the construction should be considered. After that, we calculated RA, the thickness of the breakwater, that was 1.04 meters. Actually, the thickness is from here to here. This is the RA, or thickness. And after that, we calculated the RF. When we sketch the section, should consider this is RF from here to here. And don't forget, we calculated, you do remember, cotangent theta in calculation, we consider 2. So if this is 2, this is 1. Here we should have the same. If you measure the angle, this is 2, the other is 1. It means tangent theta is 2. Overall, we have designed the breakwater. The berm details the height of that. It is 2 times, you see here, the berm height is 2 times RF. And the width of that berm is 3 RF. Therefore, toe berm, the weight of material, it was W/10. It was 0.333 tons. The height of that, it was, as I showed here, it is 2 RF, because RF we have, RF was 0.54. Therefore, 2 times that is about a little more than 1 meter. And the width of that is 3 RF. It means something more than 1.5 meters. Therefore, the dimensions and the weight of the units used in the berm is calculated. I think everything is calculated. Now, you know, when the wave comes, the highest level should be protected. Here, the wave when comes should not have normally overtopping. If there is overtopping, should be very low. In design, in the section, you consider you have low overtopping or high or what. If we have the maximum, the crest of the, for example, armor layer is not enough to withstand the wave, sometimes we put one parapet wall here that it has an L-shaped section, parapet wall. And in this case, the wave even can go up to here as well, and then is prevented. Therefore, don't forget, all this history was about the seaside. In lee side, we should have very small waves, less than 1 meter height. Why less than 1 meter? Because otherwise the ships cannot berth, they cannot download the load from ships, and they have problem. Or sometimes they are damaging the jetty. Therefore, we should be careful. And how we calculate that wave inside is 1 meter? You will see later. We have diffraction. Diffraction when wave comes inside the basin of the harbor, the gaps between 2 heads of 2 breakwater branches, you calculate what is the diffraction patterns we have. We see what is the wave inside. I will show you later very well, and you see that. Therefore, this we calculated the values, we sketched the section of the breakwater, but this is trunk. Don't forget, this is trunk. It is not for head, it is for trunk. Therefore, I hope you saw everything. For seeing again all the dimension better, let me erase all the things that I sketched here. Yes, now this is the section. If we review again, you see the W, the weight of armor, thickness of armor, RA, W/10, the filter unit weight, and toe berm unit weight, and RF, the thickness of the filter layer, 2RF, the height of the toe berm, 3RF, the width of at the crest of toe berm, and we calculate this. So the C is, we have considered the minimum 3 meters. If we have considered 3 meters minimum, we should apply parking each 50 meters. That's a must. Either for C, we consider at the beginning 7 meters and is very big material needed, or is better, we consider C 3 meters and then we put each 50 meters on the length of the breakwater, one parking. At the period of operation period, for example, we need with car and with, I don't know, track, go on the breakwater. But that times there's not a lot of traffic going and coming. We go there and prepare and come back. Therefore, 3 meters is enough. If you have a very big, for example, harbor, and you know that you have traffic on the breakwaters, you should put 7 meters. If not, 3 meters plus parking at each 50 meters is enough. And in dimensioning, don't forget the level of the design water level we should consider. I told you it's better we consider MHWL, mean high water level. And then the others is clear. Something that I should seabed layer is not strong enough to stand against, resist against material we put there. And everything we put there, it sank on the mud. What we should do? Sometimes before construction, the breakwater, they remove the soil under the breakwater. They remove this part and they put the better material there. And then they put actually one foundation for the breakwater. This is one method, and we in the Bandar Abbas, for example, port in Iran, in Persian Gulf, the section was that. It was very, very loose mud there. They first removed that, replaced by better material, and then started to construct the other body of the breakwater. This is one thing I wanted to mention. The other thing that I should mention is that sometimes they use one layer here, just one layer, that is some material that is called a geotextile. Imagine that you put some very strong clothes here, something like, and then when you put the material here, it prevents to go to the mud here, sink it there. Therefore, this is geotextile they use here. Therefore, either they improve the soil under the underlayer, of the breakwater by sometimes injecting some material there or some replacing them or by using geotextile under them. These are the methods that is normal in practice. Now let's go and see the head of the, this is head, sorry, it should change that. Let's see the head of the let's see the head, design of head. For design of head, again, everything is the same. Why it comes here? Let me see. It was not replaced the last slide. Is the old version. Sorry. For the head, we have the same table. Again, we have Dallas. Therefore, here, armor layer is selected as Dallas in the first column. We have 2 layers in the armor layer. Therefore, N is 2. We have the method of placement, random method. Therefore, we are here in the row of Dallas. And also, this is the head, not trunk. This is head. Therefore, we go here and see the head. When we see the head, let's see what is the condition of wave. Wave is breaking wave. Therefore, we go and select the breaking wave. Therefore, from here, we go down. And from horizontally, we continue and go here. Therefore, in this column, we have breaking waves. We have at head from here. And from here for Dallas, we go and find, we have 2 values, one 7 and one 8. Which one depends on our cotangent theta, the slope, which is 2. Which one is 2? The last column is a slope, cotangent theta. Therefore, you see that 2 is, this one is 2. Therefore, from here, we come here, not from 3, and we select this 8. Therefore, for us, KD equals 8. This is the conclusion. And what else? Therefore, the KD is different. Therefore, we design again the W over 10, all of B, RA, RF depends on the formula. We repeat actually the calculation from here. Just the KD is changed. The others are the same. After that, you calculate W, apply SR, etc. You calculate B. You calculate RA, RF, and then you calculate NA over A. and even NA/1, you find the unit of that. And sketch one section which is full with symmetry. The armor layer continues here, goes here. You know, because it has two sides. Even you have berm here. Exactly similarly, you have berm, toe berm here. And you have armor layer everywhere. These are armor layers. Here you have. Because at the head, it's not supported to the other section. They are subjected to the wave and supported by water, nothing else. Therefore, because of that, we should have one section like this. Let me erase this part. I continue. At the end, for the head, as I mentioned, the cross section is symmetric. You see here, you have like this, goes and go to the other side. You have armor layer and filter symmetry, and here. And this is called, as I told you, let me draw with another color. There is one layer here that is shown by yellow. This is bedding layer. What is bedding layer? Bedding layer is a layer on the soil, on the seabed, that make a little modified the soil. Its role is exactly like the lean concrete that you put under the foundation of the, for example, buildings. You put 10 centimeter lean concrete under the foundation. You put one under layer here. This bedding layer or under layer we put here. Therefore, I hope you got all the things that I told you. Let me, for reviewing, I'll go to the first slide and come back to be sure that you got everything in the example that we have. Example, they given some values H10, given the type of the armor layer, which is Dallas, is from concrete, the unit weight is clear. The breaking wave condition, not non-breaking wave, and seawater unit weight is given to us. Therefore, let me make it erase everything. And here we found KD for trunk. And you remember that we selected first the armor unit, the number of layer, the method of placement. Where is that? In trunk. And what is the condition? Wave breaking. And we found the value for KD. here we calculated W by applying everything that we had. KD we had, SR we calculated, the value of H was given to us, and the unit weight of armor unit, which was concrete, we knew that. We found W. For B, we need one K delta factor that we found from the table. And also we found the porosity for estimation of the material. Here, we calculated B, the crest width, and then we calculated the RA, which was the thickness of armor unit layer. We found the thickness of filter layer, and we found the WF, which was the weight of one filter stone, and RF, the thickness of the filter layer. We calculated the density of the material placed. How many armors we have on 1 square meter? Or one armor takes how much a square meter? We calculated that. It was MA. We used the K delta from the same table that we saw that. We use porosity percentage and the other parameters. And we sketched the section of trunk. Don't forget, when you sketch, you should give all the specification. You should give the dimensions, the heights, the angles, the sizes, the weight of each unit. For example, armor unit, filter unit, toe bearings, core material, everything should be well defined. In addition to that, the level of the crest of the core, which is fixed to the seawater level, that we considered as MLWL, mean MH, mean high water level. And here, let me erase this one. For, I told you this is mistake. It is head. I don't know. I didn't apply the last version of my presentation. And we found different KD for that. And then we should start from the beginning, calculate all parameters similar to that we did for trunk. I told you this section should be at the head, should be symmetry. We have armor layers both sides, at lee sides and C side, both sides. And that's all. Therefore, let me see, do you have any question or not? Don't forget, work on paper, because the semester is finishing. I am waiting for that, and search in the internet to find more items to understand better the course. Okay, let me see, there is any chatting, I am cutting the presentation here. Let me check for chatting. Yes, we can see. Yes, Professor, we can see it. Abdullah hit something. Dear Prof, Jean-Pierre cannot attend in the class. He'll get joined. Okay, John. Okay, no problem. Mahdi says, thank you for your explanation. It was clear. You're welcome, Mahdi. Therefore, okay, you understood that I am cutting now the recording, and we continue talking, and if you have any ask question there.